Dr. Vikas Yadav. In my PhD, I have worked on microchannels,
Okay.
heat enhancement through microchannels for cooling purpose.
Okay.
So I am now trying to use nanofluid
Oh,
inside that microchannels.
okay, okay, I see. That's
I
good.
am from Pune.
Pune.
Right now I am working in Nutan Maharashtra College of Engineering, Pune,
Nutan
Maharashtra Institute. Yeah.
Maharashtra. Okay, I see, I see. Okay,
Okay. Thank you.
thank you, thank
Good morning, sir. Myself, Dr. Digvijay Patil.
you.
I am working in same college,
Yeah. Okay,
and research area is related to composite material.
okay, I see, I see. Thank you.
Sir, good morning, sir.
Good
This
morning.
is Shrikant, sir.
Yes.
I am working as assistant professor in Rayalaseema University, Kurnool, Andhra Pradesh, sir.
Okay.
Now I am in the research scholar in under the guidance of Venkatesh, sir.
Okay.
My research topic is microwave processing of polymer matrix composites, sir.
Okay. Okay.
Thanks.
Thank you. Thank you. Okay. Any other participants? Yeah, please. Yes. Okay. Yes. Okay. Okay. Thank you. Thank you. So I just want to know what is your background. Of course, most of you are working or eager to work on the nanomaterial. So nanomaterial is the core material for most of you. And second topic for this course is types of nanomaterial. In earlier, I told you that there are two important factors that govern the property. Of course, there are several other parameters that can also control the property of nanomaterial. So nanomaterial can be divided into several type of material, and that material we call classification of nanomaterial. So first talk was just the introduction, and I can see most of you are working on nanomaterial. So how much you understand the nanomaterial? Which one of the following material cannot be seen by a simple microscope? Please listen the question carefully. Which one of the following material cannot be seen by a simple microscope? Okay. I got two answer. One answer is correct. Simple microscope. Okay. Simple microscope. Which material cannot be seen? Cannot be seen. Okay. So bulk material means you take this one, okay, and put in the simple optical microscope. You will see something. You will see something because optical microscope can gives you the information up to micron level. Okay. I'm talking about simple microscope that has lens up to 200x or 300x. But you cannot see nano material, okay, nanomaterial. That's why the size is so small, you have to use the other equipment such as scanning electron microscope or transmission electron microscope if you want to visualize the nanoparticle. So this was the tricky question, okay. Which one of the following is the example of nanomaterial? Nanosilica, sand, cement, all of above. Nanosilica. Anyone has a different answer? Nanomaterial, nano. Now sand, you go to the beach and you see the sand. Those are not, some particle may be nano if you see the dust on that, and if you are considering that will be, but what you can see, they are in maybe few micron or even millimeter. So sand is not nano, no way. Cement particle not in nano actually, if you, because those particles we can see by our eyes, okay. By the way, our eyes can see any particle up to 2.2 millimeter, that is 200 micrometer. If there are two particles, this is one particle and this is another particle, and if you put them together, okay, and both particle size is 200 micrometer, you put them together, okay, like this. Now this is one particle, this is one particle, and try to see by your eyes. You will see those two particles separately, okay. That is, our eyes has the, you know, maybe level, or you can say ability of our eyes to see something separately. But if the size of this nanoparticle and this is 100 micrometer, you join together, now you will not able to see these two particles in a separate. What you will see like they are connected to each other. So that is our eyes, you know, resolution, we cannot go beyond that. Up to 0.2 millimeter we can see the things clearly. So in cement there may be mix, not really nanoparticle, they might be microparticle, because our eyes can see. If they are nanoparticle, our eyes cannot see. Our eyes cannot see it. The gold bar and silver bar are the example of bulk. So this means you have seen lecture number 1 carefully. There I have shown you bulk gold, and this way you are understanding. So these bars are bulk, not nano. The color of nano gold particle is yellow, orange, red, or variable. Variable. Good. So this means now you are getting the things. Of course, you already study, but it's interesting to cross check whether you are understanding it or not. So variable means gold nanoparticle can be seen in different color as per their size. Quantum dot can be used in opto. Okay, quantum dots, very small particle. Okay, 2 nanometer to 10 nanometer. These are the ideal size of quantum dot. So they are mostly used in optoelectronic, because opto is light, and quantum dot behave differently when they are in this size 2 nanometer to 10 nanometer. So those quantum dot, most of the quantum dot is used in optoelectronic for emitting a different kind of light due to their band gap. Okay, that was a quick quiz for you to make you live and review our earlier talk. Let's move to the types of nanomaterial. So type of nanomaterial is classified into 4 types: 0-dimensional nanomaterial, 1-dimensional, 2-dimensional, 3-dimensional nanoparticle. Now what is 1-dimensional, 2-dimensional, 3-dimensional material? There is 4 and 5-dimensional, but our research is limited up to 3-dimensional at this moment. So we will study one by one. What is 0 dimension? What is 0 dimension means? What is 1 dimension means? What is 2 dimension means? And what is 3 dimension means? So 0 dimension is the first type of nanomaterial. 1 dimension is another type of nanomaterial, and 2-dimensional material is the third, and 3-dimensional is the fourth material. Now here this green part, okay, this green part is considered as a 0 dimension. But you start with one point, okay, one dot. You put one dot. I don't know whether they have some pen here. Okay, so when you start with the one dot, green one. Connect one dot with another dot, okay, one dot and another dot. This one dot and another dot is connected. So when you connect two dots, then it become one dimension, okay. So you started with one single dot and you connect those two dots by certain length, certain things, or combine them or join them, then it become one dimension. Like you are making the chain, okay. So how you make the chain? You make one circle, okay, and then you add another circle, then third circle, and this chain increases. Similarly, one dot, another dot, third dot, you connect 1 to 2, 2 to 3, and expand. That is one dimension. Two dimension. So now you have this, single length or maybe up and down, but it is one length, whether it is in zigzag or straight line. One dot, two dot, three dot. So this is one line. When you connect this one line, for example, this line with this line, when you connect one line with another line by something, then it is two dimension. So in two dimension, you connect one line with another, and you have connected. So this become two dimension. When you connect two dimension one unit with another unit, it become three dimension. Now what is the example? What are the example of this one dimension, zero dimension, two dimensional, three dimension? That we are going to see. But why this nanoparticle is considered as a zero dimension, as a one dimension, as a two dimension? In case of zero dimension, they are dots. In case of one dimension, they are in one line. Like you can have one rod, but it can grows in one direction only. So this chain will increase either in this direction or either in this direction. It cannot grows in this direction, it cannot grows. Why? Because this zero dimension dot is a basic dot. It will not increase its size. It will not be bigger, okay? If it is a quantum dot, for example, 2 nanometer, so it will not increase its size. It will not grow in X, Y, and Z direction. It will be as it is, okay? And when that as it is particle you connect it, you make a chain. That is one dimension, okay? So chain line. And layer. The classic example of two-dimensional material is, let's consider any paper, okay? So if you have paper, that paper will increase in X direction and Y direction, X direction and Y. So paper can be extend, okay, horizontally or vertically. So like this is the paper, okay, or let's consider this is one paper, but it can increase in this direction and this direction. But we cannot increase the thickness. We cannot increase. If you increase the thickness, it will be no more paper, okay. So two-dimensional means it can extend, it can increase in two direction. That's why it is two-dimensional. So if you are playing with the nanomaterial and it extend in X direction and Y direction, two-dimensional. If it extend in X direction, Y direction and Z direction, then it is three-dimensional, okay. So when another slide will come, you will understand how this nanoparticle is classified and why they are called as a zero dimension, one dimensional and two dimensional. So no, it's dot. It's, quantum dots, it's dot. Basically, it's single unit, okay? Because when you consider chain, okay? chain is one unit, but it is made up of small, rings, or maybe simple small unit or small point you connect with each other. Okay, so that make a big chain. Although we called it as a chain, but they are bind with something. Okay, like, do you remember I told you about the pencil? Okay, so when you rub the pencil, it is a graphite, three-dimensional. Okay, but the sheet that is two-dimensional, carbon sheet and another carbon sheet is attached to each other, and that makes three-dimensional. Graphite is a three-dimensional structure, but when you rub, what happens? This sheet and this sheet is connected, but this connection is broken, and this sheet becomes separate, this sheet becomes separate. So this way you create the carbon particle, or maybe graphene. Okay, because graphene is nothing but this sheet. If it is connected, it becomes graphite. So three-dimensional can convert into two-dimensional if the bond breaks. This way, one paper, XY direction, that is two-dimensional. And this third one, you can have two-dimension, one paper. You connect one paper with another paper. This is one paper. If you connect another with certain bond, then it becomes three-dimensional. Like, you take your smartphone, it is three-dimensional. You take rubber, anything which has X, Y, and Z. If it has thickness, then it becomes three-dimensional. Here there is no Z direction. We are not considering thickness. Okay, we are not considering thickness. Here nothing, not thickness, not width, not nothing. Dot means dot, finish. So that's why it called as a zero. There is no way it can extend in any direction. That's why it is zero dimension. So let's move to the next slide. This way you will understand if you don't understand the first slide. The bulk material is bulk, okay? Bar of silver Ag. Anything which is in your hand and it has X, Y, Z axis, X, Y, and Z. X, Y, this one is Y, okay, this is X, this is Y, and let's consider this is Z. So if it has, or there is a possibility that this bar will increase in three directions, 3D. If you cut this into the pieces this way, then it is two-dimensional. Now what you are doing, basically you are cutting this axis, okay? Earlier we were considering this axis, but you are cutting this into the several pieces. Now here, this axis is become negligible. That's why it is 2. Now possibility that it will extend in this direction and this direction only. Because this direction you already, make it into pieces and vanish. And then next you cut this part from here, okay, and make it like rod, okay, rod. So this is one dimension. And this you again cut into small piece, then it is zero. So this way you understand we have big bulk particle that is 3 dimension. You cut into one direction, then 2D. You cut, again reduce 2 to 1, and from 1 you again cut it into 0 dimension. So this way you can see what the particle size, how they classify into a particular class like 3-dimensional, 2-dimensional, and 1-dimensional, 0-dimensional. So these are the way you should understand how nanoparticle is created when they make. I told you, you should understand nanoparticle. When you are making the nanoparticle, if your nanoparticle start with bulk material and convert into quantum dot, you should understand physics and chemistry, how this nanoparticle is created. Do not concentrate on the last part. You should concentrate how these things happen. That is the research. Making nanoparticle is also part of research. Understanding nanoparticle is the real research. So try to understand what physics, how reaction happen, how this wall is break, how this rod is created, how this quantum dots is created. That is the real research. So why this kind of different nanoparticle is required, whether it is 3-dimensional, 2-dimensional, 1-dimensional, 0-dimensional? Because they can be used for a particular application depending on their properties. So each bulk material also possible to use for several. We are using traditionally bulk material everywhere. So that is no way that we can going to reduce the bulk. Bulk material has application, like I show you the airplane. So we cannot deny that we are using the bulk material. That is there and we will use it forever. But bulk material convert to 2-dimensional, certain application, 1-dimension, certain, 0-dimension, certain application. So it will depend on their property, what kind of property they exhibit. To understand it in a simple way, like we have again smartphone. So sometime this smartphone, some smartphone give quick response, okay? So when you scroll down, it give quick response than other. Or maybe 2007, iPhone was launched for the first time. And the touch technology was invented, or it was maybe come into the market for the first time. So what happened actually when touch screen become bigger? Now you can see that this thing happened, but have you understand the physics behind it? Why this touch technology is improved, whether for smartphone or whether for notebook, mobile, desktop, any kind of PC or monitor. The performance is better, the touch screen is better. That is, by your eyes you can see. But how it has been improved? It has been improved by the material that sense. When you touch your finger, the sensitivity time is less. If the sensitivity time is less, then the touch performance or it can improve. So it is the material property. It is the material property that performance. And we are always in the search of material that shows high performance. This is one of the example. There are several examples. Smart window, certain kind of material can be coated for something to reduce corrosion, to reduce the maybe blocking the UV. There are several examples. So one of the example is this: by reducing the particle size, improving their performance, either by reducing their size or adding something so that the property can be changed. Now I was telling you about the 0-dimension, 1-dimension. I believe that you understand the concept of 0-dimension, 1-dimension and 2-dimensional. So this 0-dimension means all dimension are in nanoscale. Remember, okay? 0-dimension means all, everywhere, X, Y, Z, it is in nano. It is in nano. 1-dimension, okay? In 1-dimension means actually 2 directions, okay? 2 directions are in nanoscale. That I will show you in next slide. Then 2-dimension, 1-dimension is nanoscale and 2-dimension is microscale. 3-dimension, that is most of the bulk material. Chances of expanding, increasing in 3 direction, you can make very big. No dimension, it has on nanoscale, okay? Remember, for 3D material, okay? These are 3D material, pencil, graphite, 3D material. Okay, their length is in not nano. They might made up of nano, but their whole length is not in nanoscale. So we are going to see them how these nanoparticles can be made in a certain dimension. So for time being, this is the density of state. It's a real physics about the two dimension, zero dimension. Means what happened when we think about three dimension, two dimension, one dimension and zero dimension, how this density of state affect the property. So density of state is a function that describes number of state available in a system and essential for determining the carrier concentration and energy distribution. If you remember, I was telling you about the reactivity. So if you want to understand the density concept, if you are not physicist, just remember that how many charge carrier is available for reaction. That way you can correlate this one. So number of carrier, that carrier means certain carrier is available in all material, and energy distribution of those carrier within material, within semiconductor is nothing but the density of state. So as per these kind of material, 2D, 3D, it changes. This is the example, okay? Zero dimension means it's almost circular. They are not connected, although I have shown you here, they are not connected. They are individual particles. And this is nanofiber, nanotube, these are rods. So it can extend in one direction, okay? This rod goes here, here, here. No problem. It may be 1, 200, 1 millimeter, no problem. The key point is this one, okay? This one axis, okay? The diameter will be in nanoscale. Length will not be in nanoscale. Diameter will be in nanoscale. Here, this and this will be in nano material, but nanoscale. Two dimensional means thin film, coating or sheets. These are two dimensional. X and Y increase, okay? Two direction can be increased, Z direction cannot, because we are not concentrating on the thickness. This thickness will not change. This thickness will not change, but it can extend in this direction too. And 3D is like this. So X, Y, Z, and you can connect those blocks together, make big things. That is three-dimensional. So it is basically many crystal. Those can be connected to each other and it becomes three-dimensional. And these are the real example which has been taken from the research paper. So zero dimension, especially nanoparticle, okay? Especially nanoparticle. One dimensional, it may be nanotube or nano wires like this, maybe hollow or filled with something. Two dimensional, basically sheet-like structures or these kind of nanoplates or nano belts. So either it has a special shape or maybe belt-like or sheet-like structure. So this will increase in two direction, and these are building blocks kind of structure, that is 3D structures. So zero dimension means which type of material? Zero dimension means it is a dot, it is a particle, and it cannot extend in any direction. There are various nanoparticle, nanomaterial, those called as zero dimensional material can be prepared in the laboratory. They might be amorphous or crystalline. I hope that you understand the difference between amorphous and crystalline. Today, first talk, slide number 3 or 4, maybe 4 or 5. I shown you that atoms arrange in certain order, okay? and atoms arrange not in certain order, they might have defect. So randomly arrangement of the atom is amorphous, like powder, okay? They cannot bind together. And crystalline is a solid crystalline material, like sugar has certain shape, graphitic has structures. So if you measure their XRD, you will get strong peak. But if you measure the amorphous peak, it will not be a straight peak. It will like hump kind of structure. So this is the difference between amorphous and crystalline. So those particles might be amorphous or might be crystalline, but they are zero dimensional. So it may be single, it may be polycrystalline. So individual particle might be found separately, or some particle might be connect to each other, okay, like this, might connect to each other. So their connection might be loose, or they are just laying on each other. And it can be composed with single material or multi or nano composite. Maybe you can combine one element, another element, make a composite. It is possible that one quantum dot, another quantum dot, you can make heterogeneation or combine or binary, or you can say composite material from two different kind of elements. Various shape and size is possible. So quantum dot also has shape and size from 2 nanometer to 10 nanometer. It exhibits individual or incorporated in a matrix. So you can make it separately, or you can put this zero dimensional nanoparticle into separate nanomaterial. Those nanomaterial might be 3-dimensional, 2-dimensional, or 1-dimensional. You can use this zero-dimensional material for making nanocomposite material. And they might be metallic, ceramic, or polymeric. So there are many different elements. It may be metallic, zinc, Au, Ag, tin, tungsten, or ceramic, any oxide material, or polymeric material. It is possible to create the quantum dot or zero-dimensional material. So here you can understand this concept. They can be found in various shape and size. So nanomaterial is 1 to 100 nanometer. But quantum dot or zero-dimensional material, they are the individual material. Usually their size is 1 to 10 nanometer when we talk about the quantum dot. But some nanoparticle has bigger size and they cannot extend. They cannot extend because what happen when they grow in the single unit, their single unit might be 20 nanometer, and after that they cannot increase. So ideally quantum dot is 2 to 10 nanometer, but in some cases some nanoparticle might have a bigger size. And this zero dimension can be found in different kind of shape also. So remember, they cannot extend in any direction. Okay, so both x, y, z direction will be limited for them. It cannot extend further. And their size will be always less than 100. So these are one of the example of these nanoparticle, which we call them as zero-dimensional material. Zero-dimensional material, and this zero-dimensional material, they are single line or polycrystalline, or maybe they found in single unit or maybe multi-unit. They can be metallic, ceramic. Those kind of material might be amorphous or crystalline. And this is one of the example you can see on the nanotube. These nanoparticle can be grown. This is another zero dimension. So here they are single unit. they are single unit. Okay, once they form, they cannot increase their shape. They cannot increase their shape. That's zero dimension. They're zero. And AU is the classic example that can be shown to the student to understand if their shape, size change, how their optical property change. Then next one is one dimension. You connect one dot with another dot, it become one dimension. It become one dimension. What is the example? Any kind of nanotube, like you are making chain, okay? You are expanding in one direction. Or a rope, you consider rope, okay? Or wire. So wire can be extended in one direction only. So that is one dimensional material. So those also has the same size. And example, wires, nanotube, nanorods are the example of one dimensional material. It can be amorphous crystalline. Here also same like a zero dimension. Single or polycrystalline is possible. Chemically pure and impure. Which technique you are using, depending on that, it may be pure or it may be impure. If you are using chemical reaction, sometime you might get some byproduct, impure. If you are using some kind of physical technique in the vacuum or in the liquid medium, you get totally pure material. So which technique you use for synthesis, that decide the quality of the material. And another, like you can use this material to make the nanocomposite, again metallic, ceramic, polymer, all type of material that can create the one dimensional material. But most of the one dimensional material are oxide material. So whenever you read or see the paper, most of the material is oxide or maybe individual metals. So this is the one dimension, okay? So only one will expand, and these are the examples. Length will expand, but diameter will intact. Diameter will never change. So why this diameter is not going to change? Because when you want to extend the rods, the rope, the tube, this tube, rod or rope cannot extend in this direction. If you try to extend, the shape will collapse. And the growth will be uneven. So that's why these kind of shapes are special shape, and we cannot extend, increase their diameter. If it is 100 nanometer, it will be 100 for all the cases. Even though this length is, let's say, 500 nanometer, it might be 1 micro, 2 micro, 10 micro, but diameter will remain as it is. That's the special property of one dimensional material. So to understand this, you can consider carbon nanotube. So this carbon nanotube diameter remain as it is, even though they are double wall, multi-wall carbon nanotube. No matter how many layer inside that, 1, 2, 3, 4 rings, how many, doesn't matter. But overall this diameter intact, and this length can be changed. So here nanotube, nanofiber, nanowires, nanorods, examples of the one dimensional material. This carbon nanotube was firstly invented by Professor Ijima in 1991. Carbon nanotube is very good material. However, its property was limited for certain application, and unfortunately it cannot grow that much as it is expected. After this carbon nanotube, graphene was first invented in 2005, and it got Nobel in 2010. So after 2010, everybody is doing the research in the field of graphene, and they totally forgot carbon nanotube. Otherwise, after the invention of graphene, carbon nanotube is almost vanished. Very few people are doing the research for special application. So this is the examples of one-dimensional material. Nanotubes might be hollow or maybe filled with someone. So these are more example fibers. Earlier was tube, okay? This is tube and fiber. So tube, hollow, okay? This is hollow, nothing, empty. And fibers, like fibers, okay? These are the example, and they have certain maybe diameter. Length may be big, you can see this big, okay? So this is 10 micrometer, okay? This scale from here to here, it is 10 micrometer. I'm not sure you are seeing, but this is 10 micrometer. So if you consider, this may be 70, 80 micrometer. But look at the diameter, it is 0.5 micron, that is 250 nanometer. So diameter is not changing, length will increase. Like you have many ropes and they are entangled with each other, or they are connected to each other, but their diameter is same. There are more example of one-dimensional material, nanowires, nanorods, nanotube, nanobelt, nanoribbon. So these are example. It can grows in one direction only, next class of nanomaterial is two-dimensional nanomaterial. Two means two direction, X and Y. So those material can look like sheet or plate like structure. Plate has certain width and sheet don't have that much width. So it include nanofilm, nanolayers, nanocoating. So nanofilm, you can deposit certain nanofilm of two-dimensional material, or nanolayers, you can coat nano coating, certain thickness of material you can just make or use the coating technology to coat a certain material. So it may be thin film, it may be coating, or it may be just a single layer. So two-dimensional, again same as 0 and 1 dimension. It may be amorphous, it may be crystalline. Various chemical composition, you can make those material. Why various chemical composition? Because we use a different kind of bulk material or chemical, mix them together, and we might have various combination. It can be grown in a single layer or multi-layer structure. So single layer means, imagine, single layer means it has only one layer, like sheet-like structure. So sheet-like structure, paper, and multi-layer structure means you can imagine one paper, another paper, number of paper on each other. So most of the two-dimensional structures are found in layer, one, another, like you are putting 10 paper on one paper, another paper, third paper, like this. So you are making the group of 10 paper, 20 paper. So they found in multi-layer structures. Of course, they are not attached to each other, but they are just laying on that. Okay, they are just laying. They are not connected to each other. They are loosely just, they are laying on top of one another. So those can be found in single layer. If you are using like physical technique, you can make single layer. But when you make the chemical technique, so in chemical process is continuous. After formation one layer, another layer also form, then third layer also form. and it can deposited on various substrate. It can integrated with matrix structure, means multi-structure, composite material. Again, metallic, ceramic, polymer structure is possible. So this is two-dimensional structures, and two-dimensional, as we learn that it will grow in two direction. It will grow in two direction. Okay, x and y, x and y. So any structure which is look like sheet or paper, it is two-dimensional structures. One dimension, it at nanoscale. Is only one dimension is at nanoscale. Other two will not be, because this x and this y will extend. Okay, so that will be no more in the nanos. However, this part will be nano. The thickness of that sheet will be nano. Like this. This part will increase, but this will not increase. So this length, x direction, y direction will increase, but z direction will not increase. It will remain intact, and usually it will be equal to 100 or less than 100. Then and then it is two-dimensional material. So two-dimensional material is widely researched by the researcher all over the world because of their special property. So these days, most of the research paper is on two-dimensional material. Why? Earlier, one-dimensional material, mostly oxide material, already studied. And when the invention of graphene occurred in 2010, after that people started to work on various two-dimensional material, and they are getting better performance, better research. That's why two-dimensional material is more popular than one-dimensional and zero-dimensional. Of course, they can be useful to make the composite. Take a two-dimensional material, add one-dimensional material, zero-dimensional, make a ternary composite, and improve the performance. Whether you are talking about the hydrogen production or photocatalysis or any type of maybe application, combination of this two-dimensional, one-dimensional, zero-dimension definitely improve the properties. So two-dimensional material are the special material, and those material can be used for a certain application. So these are some of the example. Let's consider this kind of example. It may be look like sheet or petal of flower, okay, petal of flower, or comb-like structures or platelet-like structures. So most of the structure is sheet. Most of the structure look like sheet, okay, or petal of flower. So those structures are nothing but two-dimensional structures. This is nanoplates. Plates has a certain thickness as compared to sheet. Little high thickness than the sheet material, but they are still the two-dimensional material. Then three-dimension bulk material. Most of the bulk material or x, y, z direction can be increased in three ways. Those materials are called as three-dimensional material. So three-dimensional materials are having the multiple arrangement. Why multiple? We started with one dot, that is 0. Then one dot connect another dot, one dimensional. One line connect another line, two dimensional. Then one sheet connect another, then it become one three-dimensional unit. And one three-dimensional connect another, make multi-component. Like one room, another room, second floor, third floor, it make building blocks. So this way it grows. Like if you have one thing and you want to grow similar thing, then you make this one unit, another unit. So 0 dimension, one dot. If you want to increase, another dot will come. 3 dimension, one unit, another unit. And one unit is big, another bigger. And it will keep increasing. So it look like it is a multi-storage, multi-block structures on the nanoscale, So this 3-dimensional material is difficult to make. But it has a certain kind of features or property like dispersion property, or bundle of nanowires can be considered in 3-dimensional structure, nanotube or multi-nanolayers. I told you reactivity is very important. Reactivity. So now imagine 3-dimensional means what? It is having 6 direction. If you consider one cube, so one cube that I have shown you about the reactivity, one cube is having 6 sides. So I think he brings the pen, so I will explain you by the pen. Now this is 2-dimensional structures. So in 2-dimensional structures, this part, okay, the front and back, this is available for reaction, But in case of nanocube, one side, another side, third side, fourth, fifth, and this front is 6. 6 side is available for reaction. 6 side is available for reaction. Remember sugar example. So if 6 side, 1, 2, 3, 4, 5, 6 side is available for reaction, so the performance will increase. Surface area is more. So it will give the higher performance. But if only 2 dimension, what will happen? For example, if you are giving energy to this 2-dimensional material, only electron on the surface of this 2 dimension will activate and try to emit, okay, only here. But here, if you give energy, the electron on each side, they will activate simultaneously and the performance will increase. So ideally, more area is available for nanocube than this one. So 4 years before, we have published one research paper that was on indium selenide. From 2-dimensional structure, we prepare nanocube, and that nanocube shows higher photocatalytic performance. This part I will show you in the green energy application, where you will understand why 3-dimensional structure is also equally important than 2-dimensional structures. So 3-dimensional structures, all X, Y, Z is possible to grow simultaneously. Now here X will grow, Y will go, and this Z will also grow. 3 direction it is grow. Sometimes this X and Y will grow fast and this Z might be slowly, but it will increase. So it will be 3-dimensional shape. Like this, okay? So all 3 direction is changing or modify. You can increase the length X, Y, Z direction, and it can create 3-dimensional structures. So 3-dimensional structures, we can control their morphology, because when you prepare the nanostructures, you understand how much size it grows. At particular temperature, at particular voltage, current, energy, whatever technique you are using, you understand the parameter, you can control their growth. Whatever size you want, your desired size of nanoparticle, you can create of this three-dimensional material, because growth mechanism is easy to understand if you are making the three-dimensional structure. When I will explain that indium selenide nanocube, there you will understand how this three-dimensional material can be useful to control their size, or easy to understand how to control the size. So this three-dimensional nanostructure is very important because of their higher surface area, okay, and all sites are available for reaction, and that's why they can use for various purposes, catalytic or magnetic or electrode material. So it is having application in energy as well as in the environment field, or maybe magnetic application. And some of the material have porosity. Porosity means some material like zirconium oxide material, they have a particular pore, those we call porous material. If you put metal particle in that pore, their performance increase. Example are nanoballs, nanocoils, nanocones, nanopillar, nanoflowers. Here you can see the example, okay. It grows in all direction, okay. If it don't grows in all direction, then it will be plate like or maybe rod or tube like structure. But when it grows in three direction. So you can see such kind of formation of particle. This is another example like low magnification 3D three-dimensional crystalline TiO2 nanostructure. So this is three-dimensional. They are attached to each other. They are not separated, okay. Two-dimensional means they are separate layer or sheet. They are separated from each other, maybe layer or maybe sheet. This is another example. So this one is AG silver. So here X, Y, Z, this direction can be controlled, okay. So to understand 0, 1, 2, 3 dimension, how will you remember that this is 0 dimension, this is 1 dimension, this is 2 dimensional, this is 3 dimensional? Dot 1 dimension. Only x-axis increase, only x-axis increase 1 dimension. X and y-axis increase 2. X, Y, Z axis increase 3 dimension. So this way you can basically understand or remember how this nanoparticle is classified and why they called as a 1 dimension, 2 dimensional and 3 dimension. If you want to see the example, if you want to see the example of this 0 dimension, 1 dimension, 2 dimension, 3 dimension, carbon is a classic example, is a good example which exhibit a different allotrope. Now, carbon, simple carbon material like graphite, we called it as graphite, it is carbon, okay. What are the different allotrope of carbon you know? Graphite is one. Other, say loudly. What are the different form of carbon? I cannot hear.
Diamond.
Diamond. So graphite diamond. Other? Any other? Any other? Allotrope means different form of same material but different form, like graphite C60. So we have graphite, we have diamond, we have C60. Other? Huh? Carbon nanotube. We got 4. Other? Any other? Charcoal. Charcoal? Yes. 5. Any other? I told you before. No? Okay. I think there are graphene. You might told I might not listen. Graphene. How about graphene? So graphene is also allotrope. Carbon has several allotrope. Okay, carbon is the most widely used material. Okay, which has various shape. Diamond, graphite, fluorine, carbon nanotube, graphene. These are allotrope of carbon. And carbon has special specification. I am not going. Initially, diamond is having a certain kind of atomic arrangement. So, if it is in diamond shape, it is hard material. You cannot break the diamond easily. Why? Because it has sp3 hybridization. The way carbon atoms are attached to each other. Okay? So, this arrangement, okay, one carbon atom, another here, this is 4, and down is 4. So, this tetrahedral arrangement of carbon, we called it as a diamond. We cannot break it easily. But one of the slide I have shown you, and here also same thing. This is graphite. Okay. So when you rub the pencil, this bond easily break and it convert into the sheet. Same material, but different crystal structure, atomic arrangement is different, property change. So that's why carbon is a special. So carbon nanotube, fluorine also different. How atom is attached to each other, you can see it make a ball, fluorine. Okay, sheet, then different property. So this bulk material, diamond bulk material, graphite bulk material, carbon nanotube, tube, okay, one dimension, two dimension, okay, two dimensional. So here you will find one dimensional, two dimensional, three dimensional of single material that is made up of carbon only. But what is the difference? You can see the difference, how the carbon atom is attached to each other, and that decide their property. So if you are making a particular nano material, you can control them. You can control them if you understand how their basic structure is going to form. Once you understand how the growth is, whether growth is happening this way, or this way, or this way, then which parameter is important? That parameter you need to change, and it is possible to control the size of your nanoparticle. So these are, okay, the example, a unique example. There might be another, but as for my knowledge, I feel that carbon is the most volatile material that can be found in 3-dimensional, 2-dimensional, 1-dimensional, and 0-dimension. So how this formation how this formation happens. Graphite convert into graphene. You are doing by mechanical force. So how this three dimension, okay, this is connect to each other. I shown by dotted, I don't know you are seeing it. Three dimension means this single hexagonal carbon ring is attached to another carbon ring. That is three dimension. But if you break this connection, if you make it, then it become graphene, that is two-dimensional material. But if this sheet, like paper, okay, paper, if this is sheet, if this sheet, you just roll it and make like tube, then it become nanotube. And if you wrap in a such a way that it will make a football-like structure. So this football-like structure is nothing but zero dimension. One element, four different allotrope, all allotrope is in different dimension. Zero dimension, one dimensional, two dimensional. So this process of rolling, wrapping or breaking occurs from the bulk material, and bulk material can be converted into two-dimensional, one-dimensional or zero-dimensional. So this way you can understand to control the size and growth of a nanostructures. So I think this will be the last slide for lecture number 2, and it is almost going to be 1 o'clock now. Let's have some question. If you have some question, we can go for question. Is there any question on classification of nanomaterials? Do you have any question? A particular type of material you want to research about their size, about their structures? Any question? Yes? Yes. If you do from big to small or small to big, okay? In the synthesis, I have lecture number 3 on synthesis. There I will teach you how we can make the nanomaterial. Whether we can go from bigger size to smaller size, or we can start from smaller and go for the bigger. Both way is possible. Okay? When you want to build one big structure, one big apartment building, you start with very small thing, you connect it and you make the big structure. And if you want to make a small structure from big, then you basically cut those parts, and if you are interested only one, then you cut everything, you remove and you got the small part. So those kind of formation of nanoparticle is called as growth mechanism, and growth of nanoparticle is possible in two ways. We call top to down or down to up. There are two ways you can make this nanoparticle, nanomaterial, and that will be the topic for, I think, class number, lecture number 3. Is there any other question? I hope. Yes. Yes. Now, when you are looking for the application, in your application, what is important? Less area is important, more area is important, conduction is important, semiconductor is important, band gas is important, light emission is important. That decide which material is better. So, yeah, so structure, because I have shown you effect of size and shape. Okay, structure means you are talking about. Yes. So each structure, let's say two-dimensional structure. Now, these two-dimensional structures is useful for various applications. Now, you will see people are doing research for photocatalysis or battery application, or they are working on two-dimensional. But you want to work on zero dimension. Which one you will choose, whether 0, 1 or 2? It all depend on their property. You have to study their property. Which property is useful? Okay? We cannot judge. First we make the material, but we never judge that this material, especially if you are making the material for the first time with different structure, it may be 1, 2, 0 dimension, nothing matter. But you must understand how it grows and what is the good property in that nanomaterial. If you understand this material exhibit a certain property, then you can decide application. It is very difficult, like you make two-dimensional or one-dimensional material and you go for certain application. Application is decided by properties. Like I'm working on photocatalysis. So for my application, I always look for the material which has high surface area. No matter it is two-dimensional, it is three-dimensional, or it is one-dimensional. It must have high surface area. If has high surface area, it can. Or other application, like I'm working on field electron emission. So there also, if you apply electricity, electron excite. So that is electrical property. How these charges, give the performance when you apply voltage or electric field to them. So that decide the application. If you make certain nanoparticle having one dimension, immediately it is very difficult to decide whether we can choose for particular application. If you do the research, like you read certain papers, and if you get certain idea that so and so material can be used for this type of application, my material is different, okay, you can go for that application. It may work. So both way, either you do the research on previous published paper, or you understand your nanoparticle and decide the application. So there are two ways you can deal with your nanoparticle. Any other question? Are you hungry? Oh, it's almost 1 o'clock. Okay, thank you very much. Thank you very much. So, thank you. I will see you tomorrow. Okay. So with this, I think